So all the nice detectiving that I mentioned in the previous slide is associated with the fact that there are certain fragmentation patterns that you can quickly recognize or begin to recognize as a mass spectrometry type person. And of course, the most fundamental of those fragmentation patterns are just hydrocarbon bits. So we'll start off looking at the mass spec of a nice simple hydrocarbon, pentane. So 5 carbon atoms in a row, looks like an extended M and so on, or maybe a spider coming straight at you so you don't see the rest of the legs. But anyway, the mass spec of this looks like this, lots of little lines. Now the things to look for, first of all, along the horizontal axis, there again is M over Z, and we always assume that Z is +1, and so what we're looking at here is these are the masses of the fragments. So we got some fragments at 27, some at 29. Go up here, there's a fragment at 72, another one at 57, and so forth. Okay. Now the height of the peaks, the relative intensity, is always determined by the biggest peak. In other words, the most prevalent fragment, and that is always called the base peak. So the base peak is assigned a relative intensity of 100, and then everything else comes from that. So our base peak here is at 43. There's another peak at 42. That is 80% of the intensity of the base peak. Now we're certainly going to read a little bit into these different heights in particular right at the end of the whole thing, and also in the next slide after this one, we're going to look how those relative heights are associated with isotopes. But by and large, we're not going to get anything massively significant out of the fact that, say, this peak at 27 and this peak at 57 and this peak at 72 are all about the same height. What we're going to be interested in is the biggest peaks and then certain other specific peaks. So anyway, let's continue on, knowing this is pentane. Pentane is C5H12. In other words, its molar mass is 72. So here is a peak at 72, and this is that M plus peak. Okay, as I said, sometimes you'll see it, sometimes you don't see it. In this case, we do see that some of the pentane made it through unscathed through the fragmentation process, and we have that little mass peak right there. Now, think about how this molecule might fragment. Okay, it was put into the mass spec chamber, it was bombarded with however we were bombarding it, and one of the electrons is going to be knocked off. Now, if there are electrons in lone pairs, those are the ones that get knocked out. But of course, in something like pentane, we don't have any electrons in lone pairs. All the electrons are associated with bonds. So we can think very, very simplistically that an electron came from a bond in a particular molecule, and that bond is the one that's going to be weaker. So let's pretend that the electron, first of all, came from this bond at the end. How will this split up? Well, let's say that it splits up so that you have the 1, 2, 3, 4 carbons as the cation, leaving the CH3, that's this little bit here, becoming the radical. Okay, so we break this one apart, it lost an electron, the remaining electron went with the CH3 and became a radical and floated off, and now we have this cation here. So CH3, CH2, CH2, CH2 plus. That would be what we would see if we saw a fragmentation there. And CH3, CH2, CH2, CH2 plus has a mass of 57. And look, lo and behold, there is a nice peak there at 57. So we've assigned 2 of the peaks so far. Here's the molecular peak right there, the molecular cation, and then here is a fragmentation in which we just lost 1 of the carbons with its hydrogens off the end, and the remaining 4 carbons with their hydrogens produced a cation. Now, let's say that it's not that bond there, but it's this bond here that got broken. So an electron was smashed out of this bond. 1 of the remaining electrons went to the right, leaving behind a nice little cation here. There's CH3, CH2, CH2 plus, and there again was the CH2, CH3 radical that floated off, and we see it no more. What's the mass of CH3, CH2, CH2? And the answer is it's 43. And there's your base peak. Okay, so the base peak at 43 is associated with this propyl cation. Okay, the result of either breaking at that bond, and there's been a cation, or of course we could have broken at that bond, and that is the cation here. Okay, now continuing on, if I break at this bond, but I say that now the radical goes again to the right and the cation comes to the left, then I'm going to see the CH3CH2+. That's the cation of interest, and of course the remaining 3 carbons and our hydrogens floated off as the radical part of that fragmentation. Mass of CH3CH2+ is 29, and there indeed is a nice peak at 29. You're going to see a lot of 29s as we go through. Okay, and then finally, this is the last bond that could have broken, and that would give us CH3+, just this bit down here, and then the rest of it floating off as a radical there. And if we use lots of imagination around here, there's 15, you can almost see a little nub in there. That is that CH3+. Okay, so we've assigned kind of a little peak, poor excuse for peak, 1, 2, 3 of the fairly decent sized ones, and then the base peak, simply by thinking about how a 5 carbon chain is going to fragment. Now I said we're not going to worry overly about a lot of the peak heights, but it is rather significant that we've got, there's the molecular ion, and then 57, 43, 29, all sizable peaks, and then here's this 15 is a ridiculously dinky little peak. Okay, well, if you think about what we know about carbocations, okay, all of these are primary carbocations. Okay, this one here is a methyl carbocation. Okay, so therefore we would expect to see hardly any of the 15, because this is such an unstable little species. All of these other carbocations would be formed in preference to that. Okay, so that's the bulk of the peaks of pentane discussed and assigned just by simply thinking about how would a C5 chain fragment. Okay, it can give you all 5 of the carbons, so that's the molecular peak, 4 of the carbons, 3 of the carbons, 2 of the carbons, or in very rare cases 1 of the carbons. Okay, so that kind of interpretation is what we're going to be seeing quite a lot of the time. Before I leave pentane, however, I do just want to point out something that you'll see extensively in some cases and with a little bit of imagination in others. Right? But let's first of all consider our base peak here at 43, CH3, CH2, CH2+. See, it's got a peak 1 carbon higher. Okay, and then if we look at the other peaks that we've seen, if we look at our M+ peak, you can see there's kind of a little peak right there at 1 carbon higher. Another one, 1 carbon higher. Go down to the 29, 1 carbon higher. Okay, so all of these main peaks that we've been able to analyze have also got a sort of a sister peak, or actually it's a grand sister peak, teeny little peaks, right, at +1. And that's because while most carbon is carbon 12, 1% of carbon atoms are carbon 13. Of course, carbon 13 very important to us when we were studying NMR, hardly important to us at all in mass spec. But each of those +1 peaks corresponds to where one of the carbons in the fragment is carbon 13. So this peak here at 44 is that's CH3, CH2, CH2+, but one of those carbons is carbon 13, so it's an extra mass of 1, so it's going to have an extra peak there. It's not overly important. You don't see that +1 peak for carbon 13 hugely as we're going through our spectra, but it is something to be aware of, especially if you get to look at really, really high res mass spec at any stage. So anyway, hydrocarbons, relatively straightforward. You just think about them breaking up into all the possible fragments by breaking carbon-carbon bonds. Now we'll move on to other functional groups.